In this video, we're going to look at an idea called isomers. And after you learn a little bit about alkanes and those fundamental hydrocarbons, this is a really great time to talk about isomers, as it's a very important concept in organic chemistry and really all of chemistry, including biochemistry. But it's often difficult to kind of just give you a definition and have you appreciate what these things are all about until you see them in the light of alkanes. So let's say, for example, I was writing an exam and I said, provide a bond line structure for a molecule with a formula, and let's assume it's molecular formula, otherwise this would be a very difficult question, a formula of C5H10. Now, based on what we just saw in the previous lecture, C5H10 is pentane. So let's say that I, as in Willoughby, maybe I should clarify that because you are you and I am me. Okay, Willoughby was thinking pentane. So I make my key, and my key says this. Now, what many of you probably noticed as you were practicing drawing molecular formulas from, drawing structures from molecular formulas, is that there are often multiple answers. And so me writing, when you look at my key, you might be a little annoyed that your structure doesn't match my structure and think, what did you do wrong? And the reality is you didn't do anything wrong. If instead of, because I didn't say draw the structure of pentane, I said something with C5H10, if you had drawn this molecule works. And similarly, if you had drawn this molecule, that molecule works. Okay. And if you had drawn this molecule, that molecule works. So all of those would have been correct answers to the question, draw a structure with a formula of C5H10. Okay, so this gets into a really actually deeply important idea in chemistry, and it's the concept of isomers. Isomers are molecules, and it could be more broadly defined chemicals, compounds, salts, whatever. Let's stick with molecules though. So molecules with the same composition, that is the same molecular formula, the same composition, but different structures. So they have different structures. Whoop, excuse me, very sorry. Structures would be the 3D arrangement of atoms. And we've been practicing drawing structures extensively on a two-dimensional piece of paper, but they're all three-dimensional arrangements of atoms. And if you change that arrangement without changing the number of each type of element, you get to something called an isomer. So again, same composition, same number of elements. If we look up here, all of these have different structures. So they're different, right? Well, they differ in structure, but they don't differ in formula. Okay? They're very similar in structure and they're identical in formula, but similar is not same. Similar is still different. So each of these molecules has a different structure, and we should make note of that, even though the formula has not changed. And so that idea, a different structure, but the same formula, is what an isomer is. And what we're going to start with, we're going to look at a number of isomers. We're going to start with is constitutional isomers. Constitutional isomers. These are isomers with, isomers that differ in the connectivity of their constituent atoms. Okay, the connectivity of their constituent atoms differs. Now, whenever I see that word isomers in a definition, I remind myself just briefly, they have the same molecular formula. So isomers are molecules with the same molecular formula. So molecules with the same molecular formula. And what I always have to remind students about, and it's a really important concept, but it's something that gets overlooked a lot, is that when we're talking about isomers, we're not talking about one molecule, we're talking about one molecule compared to another molecule. So I'm going to highlight that plural S on molecules. You can't look at just one molecule and say, for example, is this molecule a constitutional isomer? I can't say that. I have to say this versus this. Are they constitutional isomers? Okay, so it's at least a pair of molecules that we're comparing to see if they're constitutional isomers. It could be many to see, are all of these molecules constitutional isomers of one another? Okay, so it's constitutional isomers describing at least a pair of molecules. In this particular example, the answer is yes. We have C5H10, we have C5H10, but if you look, the connectivity has changed. We have a straight chain that starts on the left and ends on the right, but in the right structure, it's as if I took this part of the molecule and just threw one of the carbons over to the other side of the molecule. Another way of thinking about it is this right structure has a longest straight chain of 4. So whereas the structure on the left, if you look at the straight chain, it stretches all the way out to 5. The structure on the right stops at 4. So these two molecules are constitutional isomers of each other. Similarly, I could take this and this. We know that those two are constitutional isomers versus this molecule. Okay, so all of these molecules, first of all, are C5H10. Is that right? Am I missing something? It's like H12. Oh my gosh, it's not C5H10 throughout the entire lecture. Oh my gosh, this is so embarrassing. C5H12. What am I doing? I was thinking about cyclic alkanes. Holy cow. Do I redo the lecture? This is the first time that's happened. I was looking at that one. I'm like, what's that? That's not 10, that's 12. Oh, I'm sorry. Kill me on my evals. I deserve it. Okay, so we're at C5H12 on everything. And I'm talking about constitutional isomers, one of the most annoying topics to learn about for the first time. It gets better. It gets easier. Don't worry. Okay, my bad. Very sorry. So C5H12. I was looking at that last one. I was like 3 times 4. Whatever. You get it. If I compare all of these structures, they are all indeed constitutional isomers. Back to the original question. Yes, all constitutional isomers. Goodness. All right, we're only 15 minutes into the video. Gross. Okay, so all constitutional isomers, indeed. They all have the same molecular formula of C5H12, but they differ in structure. If you look, the longest chain here is 3. Three times carbon as the longest chain. Okay, so 1, 2, 3 at that point. It's as if we took this and added a buddy to it, I guess. 2 methyl groups, excuse me, 2 1-carbon chains hanging off of the central carbon. So let's keep going. Let's consider some other ones. This is kind of not too bad. We're just taking parts of the molecule and just picking it up. Maybe I can even demonstrate if you're having trouble following this. It's as if I took this molecule and then redrew it, but I picked one of the, oh, that's not going to work. Shoot. It's as if I picked this part up. All right, you get it. It's as if I delete that part and then move it over here. I thought I could do something cool with the iPad. Not my best work, this one. Okay, so it seems fine, right? Well, let's compare some other molecules. So this molecule is C5H12, an isomer of pentane. Let's compare it to another molecule. What if instead of taking this carbon and putting it at the second carbon from left, we put it on the third carbon from left? That is, what if I draw this structure? C5H12, C5H12. Okay, they have different arrangements in three-dimensional space. It should be yes, right, but you're hesitating and you have me nervous. The problem is, if molecules can roll and tumble in the universe such that they have identical structures, they are not constitutional isomers. I know that, yes, from left, I went from being connected at C2 to now C3, right? But if you look, if we actually take this molecule and tumble it over, we get to this structure. So we have to be kind of careful about isomers, and we must avoid duplicate structures, as they are not constitutional isomers of one another. Both of these might be constitutional isomers of pentane, but the problem is I can't say both of these. They are the same molecule. I wish I could do a trick where I take this molecule and spin it this way on the iPad so that you could see. If I just kind of rotate it this way, it will have the exact same depiction structurally as the molecule on the left. And if you can roll molecules around, they are not constitutional isomers. Constitutional isomers happen when we take bonds and we sort of break them and then rearrange them to get new structures, okay? So it's C5H12 are the same, but where they differ is their connectivity. Here, both of these, the connectivity is the same. One little trick we can do is we can look at the longest chain and ask ourselves, okay, we went 4 carbons long and we put a carbon at the second carbon. Here, we went 4 carbons long on the right, but I'm going to count from not left to right, but right to left. And then I could see that I could put that carbon at C2. So we like to read from left to right because that's how we were trained. Molecules are just things that float around in the universe. They could be, they could have their chains pointed left to right for our convenience, or right to left because they don't care, or up to down, that sort of thing. So to continue on with the discussion, this molecule is the same as the other ones, because again, if you count a long chain, we continue to put that one carbon chain, that one carbon hanging off our main chain, our long chain, at carbon 2. Okay, there's a trick to all of this. I like the long carbon, looking at the longest straight chain of carbon elements and seeing where things are connected. It allows me to see how some of these structures are truly constitutional isomers or duplicate or the same structures. Is there something more systematic? And yes, there is. That gets into the idea of nomenclature or naming organic molecules. So again, very sorry about the mix-up with the molecular formula. Hopefully you were not screaming at your computer the entire time. And if you were, I'm very sorry. But that was constitutional isomers. Hopefully you can see where constitutional isomers come from. They have different structures, and hopefully you can see that molecules can have multiple constitutional isomers, but we have to make sure that we don't include duplicate structures, as they're not isomers, they are the same molecule.